Okay, I think I got everything figured out now. I got some stuff uploaded, so you should have had time now to look at a couple of my lectures from earlier this week. We are going to now, right, if we weren't to review our energy and variations, well, really the big things to remember from coming out of that information is, or out of those lectures, is this idea of the principle of virtual work, right? So the work done by external forces and the work done by internal forces, right? Adding those up equals to zero. That would make a system that's in equilibrium. And our principle of stationary potential energy says that the variation in the total potential energy, right, delta pi, is the change in strain energy, which is essentially our internal energy, right, minus our external energy, right, delta W. And that all has to equal zero if we are going to have equilibrium of our system. And so let's look at, well, how do these principles help us if we are going to develop a element, right, a finite element? Well, we've done a lot of work with bar elements, right, the bar element so far in class. So I figured we'd start with a bar element and run through the process of deriving through our principles of stationary potential energy a bar element, okay? It takes a bit of time here, and it's fairly in-depth, and it seems like there's a lot more work than should be required for such a simple element, and there is in this case because we were able to derive it with mechanics-based derivations. But this will hopefully give you a contrast. We can go back and look at our mechanics formulations versus our stationary potential energy formulations. We should get the same result, but just getting there in two different directions, okay, or two different paths. So in this case, we were going to develop a bar element using the principle of stationary potential energy. What are the assumptions of this bar element? Well, if we have this bar element, it's laid out in space like this, right? One end is the origin, for instance, right, with x and y and z coordinate directions, right? X is in the direction of the element. We have node 1 and node 2, or n1, end 2. It has a length, our element has a length L. We're going to say that our element, as you can see here, right, some assumptions is that we have a straight bar, right? There isn't any variations in geometry. We're going to say that it follows our linear elastic assumption, and that it follows, right, Hooke's law, right, which essentially says that it's linear elastic, but in this case we have some relationship between the modulus of elasticity E, right, and our stress and strain. And so if we have this linear or variational bar element, right, the total potential energy we know from previous lectures now is our capital pi for total potential energy equals our strain energy minus the work done by external forces. Well, if we look at strain energy, it's capital U, right? Like we did, for example, with our spring, right? The example with the spring looks at, right, strain energy is really, right, the internal energy, which is really the area under our stress strain diagram, right? In that case, it was our force deformation diagram for our spring. Well, now we're going to look at the area under stress strain diagram. Okay, which is really energy, right? You guys remember from mechanics of materials, a material that has a very large amount of area underneath the stress strain curve, that area is really the toughness or the energy that is able to be absorbed by the system. Well, in this case, right, so then that our strain energy becomes the area under that curve. Well, if we're linear elastic, it's going to be very similar to our spring. So we have 1/2 the stress as a function of x times the strain as a function of x, right? 1/2 base times the height being the stress, base being the strain, right? So this is our 1D linear elastic strain energy equation, right? And this is the strain energy at each point in the bar, right? At every point along this bar, if we were to apply external forces at, say, nodes 1 and 2, right? Every point along that bar at some dx or dl, right, would have some sort of strain energy associated, right? 1/2 times the stress at that point times the strain at that point would give you what the strain energy is at any point in that bar. Well, we need the total over the entire bar, right? So we want the strain energy, right? Total of the system, that is our total potential energy. So if we want the total over the whole system, we're going to say that this is the 1/2. We're going to pull the 1/2 out. The integral over the volume now of the stress times the strain over the volume, right? That's really what it is. Well, the volume, right, is really the change over the x, y, and z coordinate directions, right? Dx, dy, dz, or dy, dz, dx. It's up to you. We're going to say, so I'm going to come back here. I'm going to say, okay, well, this really equals 1/2 the integral over each of our coordinate directions, right? So 3 integrals times stress times strain times dy times dz times dx, right? Well, 2 of those integrals really don't vary with respect to, right, stress and strain. Stress and strain are really acting, if we're in a bar element, they're only acting in the coordinate direction with which we have displacement, which is along the x-axis. So really dy dz, right, sigma and epsilon do not vary with respect to those 2 coordinate directions. So the integral with respect to those 2, so we do 1/2, we can pull out sigma and epsilon. Now we have dy dz, sorry, double integral dy dz dx. Right? Well, this, right, dy dz, the integral of dy dz, is really the area, right? That's just the cross-sectional area with respect to y and z. So we're going to just replace that, and we're going to say that we get 1/2. Now we have the integral with respect to dx. Well, it's really over the length of our element, right? It's discretized over just the length of our element. It goes from 1 to 2. That total length is L. So we're going to take the strain energy, or the integral over the length of our element, or from 0 to L, of our stress times our strain times now our area, right, dx, right? Because dy dz was really just the area. Well, we can use Hooke's law here and relate stress to strain. So we end up with, well, E epsilon is really equal to stress. So now we can make another substitution. We get 1/2. Okay, wow, this iPad is getting really hot. It's like burning my fingers. Maybe I've been charging it too much. Okay, so 1/2, the integral, 0 to L. Well, now we have this relationship. So I'm going to plug that relationship, E epsilon A epsilon dx, right? So that's really strain energy. Well, in that equation, right, strain is really a function of x. So we need to relate displacement to strain. Well, we all know that the strain is really the change in length over the original length. Well, if we look at it from an infinitesimal standpoint, right, du dx, or really the first derivative of displacement, right, with respect to the x direction. Well, now we end up with a u expression, or a strain energy expression, as 1/2 the integral u bar E A u bar dx. And this is really the strain energy, or internal strain energy of the bar, right? And this is evaluated from 0 to L, or the length of our element. This is internal strain energy. Well, seems easy enough, right? Well, we got U. Well, we need work, right? We need the external work, W. Well, in this bar, for instance, the external work, well, this is when we assume, well, what kind of loading or external forces can our bar have exhibited on it, okay, by external loads, forces. Well, in this case, we're going to assume that we can have both a distributed load, Q sub x, and nodal loads on the bar, right? F sub 1 and F sub 2, which are going to be acting at our nodes 1 and nodes 2. Each of those nodes, right, have displacements U sub 1 and U sub x, all acting in one coordinate direction, right? So we know work is force times distance, so we really want to know what's the external work. Well, the external work is the force times distance of each of our external forces. Well, the ones that are easy are our first ones, right? We take our nodal loads and we say F1 times U1. Well, that's the work of the first force at node 1, right? Because it undergoes a displacement. Same goes for the second load at the second node. Well, now we have this, right, uniform distributed load over the length of the element. Well, we really need to look at how each of the contributions of that load over each of the incremental steps, right, of that element. Right, because as we go from U1 to U2, we're going to have some sort of displacement function, right? U sub x, right? U sub x between node 1 and node 2. And so we can really look at the work done by this distributed load as the work done by each of these individual components of the distributed load over, right, the displacement that the bar undergoes at each of those locations. So we really are looking at an integral now from 0 to L, right, over the entire length of U sub x times Q sub x times U sub x dx. Right, so essentially taking force times distance, where the force is what's the distributed load at any given point along this bar element, and you match that to the displacement that that bar element undergoes at each of those locations. So we have F1, U1. Well, now we can pull all of these things together, get one expression, right, for the total potential energy, pi equals 1/2 0 to L U sub I U prime dx minus F1 U1 minus F2 U2 minus, right, because it's U minus W, 0 to L Q sub x U sub x dx, right, and that is our potential energy. Well, we want to find the minimum value of our total potential energy, or our stationary potential energy. But pi is a function of definite integrals, right? Well, ordinary calculus minimizes functions. Well, we know that variational calculus. So variational calculus is our method of minimizing functionals, which is a function of integrals, right? So pi is a functional of U sub x, right? It's a function of the derivative of U sub x, right? It's a derivative of U sub x. So really, it's a good thing we know variational calculus. Right. So we can minimize it. Right. And when we minimize it, we can figure out what the point at which we are in equilibrium, right? So this up here is really, this is our total potential energy of our continuous model. Right? This is really the integral of, say, our uniform distributed load, right? Q sub x. U sub x, that work done is continuous, right? Because we're taking the integral from 0 to L. Well, in finite element analysis, right, we discretize, right? We separate this once continuous model of this element that goes from start to finish, right? Or this bar element here, right? It goes from start to finish. And we really look at it as, right, nodes with which we interpolate the value between the nodes. Right? U sub x can be possibly complex, right? Not so much in our bar element here, but right, when we're deriving lots of these, right, it could be possibly complex. Well, in the finite element analysis method, right, we no longer look at this uniform, right, continuous displacement model across the entire element or across the entire real world model, and we discretize it, right? So we're looking at the displacement of FEA, if you will, which is really the interpolation between nodal values. All right. And as we know from what we've done previously when we've derived these functions, right, essentially it's just an interpolation function. This u sub x for our FEA, right, our finite element analysis, must be admissible, right? It has to be physically possible. It means it needs to be continuous between nodes. It's got to be continuous between elements. Can't have massive steps, right? And we again must always satisfy, displacement boundary conditions. Conditions. Okay. So for bar element, if we're trying to come up with this interpolation function, right, u sub x, we have 2 degrees of freedom, u1, u2. Well, if we have 2 degrees of freedom, we know that we're going to have 2 generalized degrees of freedom to start with, right, of our function that's required. That's our limit. We can only have 2. So if we start with that, right, we know that as you guys have done in homework 2, right, our X matrix is now going to be the top of Pascal's triangle in this case, right, with respect to Y. So now we essentially just have a higher polynomial with which we have to the nth degree, right? So the first one's a constant, the first one's to the first degree, second, third, and fourth, and so on. So if we have two generalized degrees of freedom, we essentially only get to select two terms. We have this 1 and x. So now our use of x now becomes, right, a naught times 1 plus a1 times x. What we know from our experience here, right, this is really a linear interpolation function. And why are we doing this now? Well, before we kind of had this decoupling. I wouldn't say decoupling, but there's a separation of, right, our mechanics-based derivation of our stiffness matrices, and we were able to essentially calculate nodal values without our interpolation function, right? And then once we got our nodal values, well, now our way in which we are calculating energy, we're going to relate that back to, right, our displacement, especially when you have loads that are acting between elements, right? In between nodes, right? The element doesn't know what's going on there, so we're going to have to adjust and move those or calculate those based on the interpolation functions. And so we're going to have some, what we would call a strain displacement matrix, okay, that allows us to incorporate what's going on with respect to displacements within our interpolation functions, because as we know, right, the strain energy, right, that happens within our element is a function of the displacement, and that displacement is a function of how we assume the displacement acts between nodes, okay? So in this case, we're going to do a linear interpolation function. So we have use of x. Now, while we know that from our previous work, right, that we can also now move, right, our a naught and a1, we can solve for those, right? They're going to be a function of the coordinates, right, and the length and things like that. But we also know that that essentially can be rewritten in terms of shape functions, right, or known nodal values, which we would get n1u1 plus n2u2. And if we look at that, if we back it out in terms of matrices, we're going to get, right, it's n times d, right? With d is our matrix array that essentially says u1 and u2, and n is just n1 and n2, okay? So from previous bar element, when we solved that x times the inverse of big A, right, where big A was our x evaluate, or x matrices, right, this 1 and x evaluated at our locations, at our nodal locations, we get our shape functions for a linear bar element is 1 minus x over L and x over L. Makes sense? Well, in order to simplify this, Cook does this, and everyone else seems to be doing this, okay? Which kind of seems to help out, right? Just simplifying things. What we end up doing is introducing a natural coordinate. So instead of saying 1 minus x over L, right, we're just going to simplify and say 1 minus this xi, right? So this is xi, okay, which is pronounced xi, all right? Hopefully no one makes fun of me for this. There's a lot of them here as we continue on. Okay, well, what we're saying is now we're going to say xi is x over L. Well, what does that do? Well, it just kind of simplifies some things. Well, now we have 1 minus xi and xi. Right? Now is our shape functions. Right? So we're linearly moving from 1 to xi, okay, with respect to how the impacts of our nodal values, right? Because n1 multiplies by u1 and n2 multiplies by u2, right? So where do we go on from here? Well, we come up to, like I said, right, we need to get a function of our strain, right, as a function of what are our nodal values. Well, that gives us, right, our shape function give us a relationship with respect to what is our displacement at any given point, right, based on our nodal values. And so n, right, our n matrix or our shape functions really allow us to write our displacement as a function of our two known nodal values. Right? Well, our strain displacement matrix, B, allows us, as you can imagine, to write our strain of x with respect to our nodal values, right, as a function of nodal values. Well, if we look at definition of strain, right, change in length over the original length, right? It's really the same as saying, right, now that we know that U is ND, right? Well, if we plug that in here, we could say right, the change in our displacement with respect to x is really the strain. Well, that's ND. Well, however, N, as we know, is a function of xi and not a function of x anymore because we use this simplification with this natural coordinate. So we need to dig deep, and we need the chain rule, because I know all of you were thinking of that as I was, the chair rule, that's what we need. Now, chain rule. I'm sure everyone was thinking about that, right? Where we can take the derivative of something that's with respect to something else by taking the derivative of that something with respect to that variable first. Okay, what does that mean? Well, let's write this out, right? So what does that mean? That means that d dx, right, derivative with respect to x, is the same as saying the derivative of xi with respect to x times the derivative with respect to xi. Right? So if we have xi, that is x over L, the derivative of xi with respect to x is really 1 over L. So d dx equals 1 over L d xi, right? So that's what we need to plug in there. And we're going to take this, plug it in up there. L. What do you end up getting? Well, therefore, the strain is really, right, du dx, which you know now that we plug in, right, it's going to be the change with respect to x times the shape function times our displacement matrice. Well, now we know that du dx and d dx is really 1 over L, right? d xi of now our displacement, or our shape function, times our displacement. So if we simplify this, we get the strain is 1 over L, negative 1, 1, right? Because we're taking the derivative of this with respect to xi, so then everything goes to 1, right? We get negative 1, and we get 1 times u1, u2, and it's this expression right here, this part of it, that we're going to call our B matrice, right? And this is our D matrice. So what does that mean? Well, that means our strain of our system is really the strain displacement matrice times the displacements of our nodes. Okay? Well, once we know strain, we looked at, right, the strain of our bar element, and we know that it's the area underneath our stress strain diagram, right? We know that that area under a stress strain diagram is a function of, right, the derivatives of displacement, which is essentially strain. So we can take what we had previous, which was, right, strain energy just not happy with my u's, is really 1/2 the integral 0 to L, right? U bar EA U bar dx, right? Or the derivative of displacement with respect to x times EA times the derivative of displacement with respect to x dx, okay? What does that matter? Well, we have strain now, right? U bar equals strain equals our strain displacement matrix times D. This is when we use some weird matrice principles to say that our first, we're going to say, as we simplify this, this is going to help us. We're going to say D transpose times B transpose, which is essentially B times D, just in a different form, times EA times B times D dx. Right? Well, our D is not a function of x, right? D is our known nodal D is our known nodal values, right? U1 and U2. So we can pull D's out. And I'm going to just pull that to the front and that to the back. So we're going to get a strain displacement strain energy is 1/2 D transpose 0 to L BT EA B dx times D. And it's really this part that we're going to evaluate, right? Because those are known nodal values, right? D transpose and D, essentially our displacement matrix of our nodal values transposed. Right? Well, we know what B is also, right? B is way up here. It's 1 over L times -1 times 1. Well, if we do some transposing, we can evaluate this. What does that mean? Well, that means that, there we go. We get 0 to L, the integral, 1 over L. Well, now we transpose it. Well, now it's -1 and 1 sitting on top of each other times EA times another 1 over L. Now it's not transposed. It's -1 times 1 dx. What do we get? Well, we get EA over L times 1, -1, -1, 1. Right? We just got that, right? We got that before when we were doing our mechanics-based formulation for our element. And that's why we kept the D transpose, B transposes, so that all of that would come out and it would look similar. We end up with, right? That is the stiffness we got before. And it's the, right, we call it K sub E, or the elemental stiffness matrix. So if we simplify that, we're going to end up with one equation here for the strain energy. We get 1/2 dt K sub E times D. So that is our finite element, right, strain energy. Right? We're looking at discrete elements. You know, those discrete elements have known nodal values. Well, we take the fact that we have a relationship between known nodal values and displacement values to figure out what the strain energy is, which is the area underneath the stress strain diagram. So those are always good. Well, we have work too, right? Because our total potential energy equals the strain energy minus the work done by external forces. Well, if we look from previous, for our continuous model, right, we knew that the work is equal to F1 U1 plus F2 U2 plus the integral from 0 to L, Q sub x, U sub x, right, dx. Or we need to relate displacement at any given point to our, right, known nodal values or our interpolation function, right? And when we adjust this to finite element analysis work. And so what are we going to do? Well, where we have displacements, we know that those displacements are really equal to our shape functions, right? U sub x is really n dt or nd. Well, if we take d transpose n transpose, which I'll show you, there's a reason why this all works out. It's the same thing, right? So we're going to make that substitution. We're also going to pull out our F1, F2, and U1, U2 into matrices form. So we get U1, U2 times F1, F2 plus the integral from 0 to 1 now, right? Because that's what our natural coordinate allows us to do, because now we're going to say we no longer have it with respect to x, right? Our uniform load, right? Our body load on our bar element. So now we get dt nt, right? There's our u sub x. We're going to replace with our natural coordinate, because we know n is a function of our natural coordinate. We're going to multiply by L now to get that back in there. And we have d xi, right? Using the chain rule again. So what does this mean? Well, that means we have dt, right? That's our u1, u2 times f plus dt. Well, dt is not a function of d xi, so it comes out front. We still get 0 to 1, right? Instead of L, we're pulling that out, because our natural coordinate, if you remember, is x over L. So we no longer go to L, we're actually going to 1, because our shape functions, right, go 1 minus xi to xi. Well, so we're essentially going from 0 to 1. At 0, we have our u1 value. At 1, we get our u2 value. We get n sub t, q sub xi, L d xi. Well, we're going to pull out, right, we both have our nodal values transposed. So we get f plus L, that's constant, right? 0, 1, nt, q sub xi, d xi. What are these? Parenthesis. These are what we would call our energy equivalent nodal forces. Right? In our finite element analysis process, right, we're only allowed to apply forces at nodes, right? We can apply forces in the element, but then we have to relate how those forces interact with respect to the nodes, right? Because we are calculating for known nodal values, and then we interpolate that function everywhere else along the element. And so this q sub x, or essentially the surface force, right, that's distributed over the bar element, we need to figure out, well, how does that relate to, right, our known nodal or our nodes, right? So we can apply forces, right, F1 and F2 at those nodes. So that's where our energy equivalent nodal forces allows us to do that. Well, now that we have our work done, right, with respect to our finite element and our strain energy that was a part of our element with respect to our element degrees of freedom and displacements, we can look at the finite element analysis total potential energy, right? Where if we start by looking at, previously for our continuous model, we had this continuous bar element, from start to finish. We're not discretizing it. We haven't looked at the finite element. Our potential energy equals 1/2 the integral 0 to L. First derivative of displacement with respect to x, EA, first derivative times dx, minus now the work, which is both our externally applied forces times their displacements, which are nodal displacements, times our, this uniform load times its displacement at any given point, along our continuous model. But now for our FEA model, where we have known nodal values, we're going to look at our total potential energy as 1/2 d k sub e d minus dt f plus L integral 0 to 1 now, We're solving over the element. And now we're going to use our natural coordinate to simplify things, over the element from 0 to 1. And we get our total potential energy of our element. Well, our first equation, because this is a continuous model, we have definite integrals from 0 to L, over the entire variation. We would be required to use Euler-Lagrange equation, to find the first variation of pi. While the second one is no longer a function of the integral of u sub x. It has a finite number of degrees of freedom, Our d sub t, or our d matrix c, which is just transposed here, So we have known nodal values over which they act. So we can now find our variation of our total potential energy, much like we did with our 1 degree of freedom spring example, So we essentially look at what happens when we add in, a unit displacement, an arbitrary displacement. We're going to say that our total potential energy is 1/2 dt k sub e times d minus dt now times, we're going to simplify this and say f sub e. So if we look at our equation up here, f sub e is really this whole glob stuff, which is our nodal plus equivalent nodal forces. So nodal plus equivalent nodal forces. And we know that when we take the first variation, or delta pi, we set it equal to 0. We get delta dt, We're moving some small amount times d minus delta dt times f sub e. We set that equal to 0. Well, again, we can pull out our delta dt, our small arbitrary amount of displacement. We set it equal to 0 because we know when that equals 0, this being arbitrary. So when that equals 0, then our system is in equilibrium. What does that mean? Well, if it's arbitrary, we'll pull that out. That means that what's in the parentheses needs to equal 0. So we're going to say that our element stiffness matrix times the displacement minus F sub V must equal 0, or we get KE sub D equals F minus L integral 0 to 1 NT Q sub natural coordinate D xi, and we get our governing equation for our bar element. Right? So it's essentially the same equation that we got before, but now we included, right, this is our force matrix. We include now this uniform load that's acting along our bar element, okay? I'm sure there'll be questions. I'm gonna post a homework today all about calculating some potential energy and really calculating the displacement. Like I said, it won't be due till, I think I'm gonna make it due the end of next week. Reach out with any questions via email. And I will see you guys on Wednesday for sure. Otherwise, I should be up on campus earlier in the week. If you have time, swing by. I'll see you guys soon.